Hi guys, my name is Pausini and my metric number is 230909. Let's talk about the introductions. Ordinary differential equations (ODE) are essential mathematical tools in engineering, used to model and predict the behavior of dynamic systems. They relate the functions with the derivative, capturing how the physical quantities change over the time or space. Engineers use the ODE to design, analyze, and optimize the system in the mechanical, electrical, chemical, and civil engineering. Now, look at the examples. First is the cooling of an engine. When the vehicle engine is turned off, it will begin to cool down over time. This process follows the Newton's law of the cooling, which is modeled by a first-order ODE. Engineers use this equation to estimate how quickly an engine returns to a safe temperature based on the surrounding environment. Second example is the mass spring damper system, appears in the mechanical structures like the car suspensions or building supports. This system is described by a second ODE that models how the system moves under the force, including how it vibrates or returns to the rest. Understanding this will help the engineers design a stable, smooth operating mechanical system.
For purpose 1, cooling of an engine. Car engine heat up during use. By understanding how far they cool down is critical for design and safety. So for the model development, dt over dt is equal to negative k times temperature of engine minus ambient temperature, where k is a cooling constant. The car engine is turned off when it reaches 120 degrees Celsius. The surrounding air ambient temperature is 25 degrees Celsius, and after 10 minutes, the engine temperature is 90 degrees Celsius. Use Newton's law of cooling to first find the cooling constant k and predict the engine temperature after 30 minutes. For the first question, we find the cooling constant k by using separable method. So we derive the equation just now, and then we will get a linear equation where t is equal to 25 plus ce power of negative kt. And by using simultaneous equation, we sub in the value, and then we will get c is equal to 95 and k is equal to 0.0380 minute power of negative 1. For the second question, we predict the engine temperature after 30 minutes. So we use the equation that we derived just now, then we sub in the value in the equation. Where we will get after 30 minutes, the temperature is 55.38 degrees Celsius.
Problem 2, mass spring damper system. We will use second order ODE to solve the statement. We will be given one second order equations with initial conditions and difference damping coefficients, and use it to case A, we substitute C into the equations, and we find the roots is compact roots. So we use the general solutions of compact roots. After we need to find C and D, we substitute the initial condition into it. For the initial condition of ds over dt, we need to derive the general equation of compact root first. After we find C and D, we substitute into the general equation of compact roots, and we find the final answer. Since b squared minus 4ac is less than 0, so the system is under damped. Case B also same step as case A, but this time we call the roots is equal roots. So we use the general equation of equal roots to find A and B, and also we got the final answer. And since b squared minus 4ac is equal to 0, so the system is critically damped. Case is we got the roots is distinct roots. So we use the general equation of distinct roots to find A and B. And we got the final answer. Since b squared minus 4ac is greater than 0, so the system is overdamped.
ODE is important in engineering as it helps to design and simulate how the system will behave under various conditions. Besides, ODE model ensures safety by predicting maintenance needs as well as improving performance.
Hi, this is Divya, and for now I'm going to explain about what did we learn. ODEs are powerful tools to model time-dependent behaviors as it predicts reaction completion in batch reactors. It also tracks temperature spikes during exothermic reactions. Nevertheless, it's also essential for safety, performance, and efficiency in engineering, as it provides a mathematical framework to predict how system evolves over time. It also allows us engineers to analyze and optimize system behavior under various conditions.
Now we'll see how ordinary differential equations could be related to daily life engineering challenges. For the first example, we have predicting the motion of systems, for example like vehicles and robots, or vibrations for bridges and engines. So the ODE application that's used is Newton's second law, which leads to damped oscillations and rotational systems.